Now we are ready to show some particular problems not to have algorithms. The central ideas for this lecture are, first, that Turing machines can be enumerated, so we can talk about the ith Turing machine. That lets us diagonalize over Turing machines the way we diagonalized over languages, showing a particular language that cannot be the language of any Turing machine. Then we establish the principle that a problem is really a language, and we show specific problems not to have Turing machines. To enumerate Turing machines, we're going to develop a specific representation of Turing machines as binary strings. It is sufficient to provide a code for Turing machines whose input alphabet is 0 or 1, although we could encode others if we wanted to. The reason it is sufficient to assume only 0 and 1 are inputs is that Turing machine codes themselves will be binary strings. So we can focus on Turing machines with input alphabet 0, 1 as inputs to other Turing machines with the same input alphabet. The first thing we need to do is to assign integer codes to the components of a Turing machine. We give integers 1, 2, 3, and so on to the states. We'll assume that Q1 is always the start state, and we'll also assume that Q2 is always the one final state of the Turing machine. Notice that once a Turing machine enters a final state, nothing further matters, so we can always merge all final states into one. Thus, we can restrict our attention to Turing machines with a single final state and know that we can still define any recursively enumerable language. The other states will be numbered 3, 4, and so on. The tape symbols are also numbered starting at 1. We'll assume x1 is always the input symbol 0, and x2 is always the input symbol 1. x3 will always be the blank, and any other tape symbols are numbered 4 and above. There are two directions, but we need to number them. D1 is left, and D2 is right. Consider a rule expressed using the integer numbering of the components. That is, the state is Qi, and scanning symbol xj. We'll suppose the Turing machine goes to state Qk, right symbol xl, and moves in direction d sub m. Represent this rule by blocks of I, j, k, l, and m zeros separated by single ones. Notice that all the integers are positive, so the representation for a rule never has consecutive ones. We then represent an entire Turing machine by all its rules concatenated and separated by pairs of ones. Once we have Turing machines represented by binary strings, we can convert these strings to unique integers using the trick we explained a while ago. Put a 1 in front of a binary string and treat the result as a binary integer. Thus, we can talk about the ith Turing machine. And of course, we earlier learned we could talk about the ith binary string. A small matter is that some binary strings represent flawed Turing machines. For example, it might have a pair of double ones with other than 4 single ones between them. That would not represent 5 blocks of zeros and therefore would not represent any move of a Turing machine. However, let's assume any binary string that is flawed represents a Turing machine that accepts the empty language. Likewise, if I is the integer we get from such a string, then the ith Turing machine accepts the empty language. So here is a table relating Turing machines to the strings they accept. The value in row I and column j is 1 if the ith Turing machine accepts the jth string, and 0 if it does not. Notice that if the ith Turing machine is one of the flawed ones, then its rows is all zeros. Any matrix of zeros and ones with rows and columns corresponding to all the integers can be diagonalized over. That is, we can construct an infinite sequence of zeros and ones, call it D, such that the ith bit of D is the complement of the bit in position II along the diagonal. We can argue that D is not a row of the matrix and therefore does not represent the language accepted by any Turing machine. D can't be row J because it disagrees with the jth row in their jth entries. Thus, D cannot be a row, and therefore the language it describes, the language that contains the ith string if and only if the ith bit of D is 1, is not the language of any Turing machine. Notice that this language can be described as the set that contains the ith string if and only if the ith Turing machine does not accept the ith string. Let's give a name to this language, L sub D, or the diagonalization language. Again, L sub D is the set of binary strings W such that W is the ith string for some I, and the ith Turing machine does not accept W. We just argued that L sub D is not a recursively enumerable language, that is, it has no Turing machine. We earlier proved that since there are more languages than integers, and since there are no more Turing machines than integers, we already know that there were languages with no Turing machine. But now we're much better off. We have a particular language, L sub D, and a description for this language such that L sub D is one of the languages without a Turing machine. Note, however, that L sub D is a delicate language. We know what it is, but we can't, for example, always tell whether a given binary string W is in L sub D. To do so, we can figure out the I such that W is the ith string. That's the easy part. Then we can write down the code for the ith Turing machine. In fact, that code is W. If W is the code for a flawed Turing machine, we know it doesn't accept W. But some W's give good codes for Turing machines, and in fact every Turing machine with input alphabet 0 and 1 has at least one code W. We can't always figure out whether a Turing machine is going to accept or to run forever without accepting, so for at least some W's we can never learn whether or not that W is in L sub D. Let us introduce the formal concept of a problem. Informally, a problem is a yes-no question about an infinite number of possible instances of the problem. Here's an example of a problem that is actually quite famous, and we'll see why soon. The instances of the Hamilton cycle problem are undirected graphs. There are an infinite number of graphs, of course. The answer to the question implied by the Hamilton cycle problem is yes, if there is a Hamilton cycle in the graph that is a cycle that passes through each node exactly once. For example, here's a graph that happens to have a Hamilton cycle. It's also got some other edges here and there. But the important thing is it does have the Hamilton cycle in which every node appears once. So formally, a problem is simply a language over some alphabet sigma. Each string in sigma star can be viewed as an instance of the problem once we decide on an encoding for instances as strings. We'll see a number of examples of these encodings, but we already saw one when we encoded Turing machines as binary strings. It should not be hard for you to devise an encoding for graphs in a similar spirit. Then the language associated with the problem is the set of strings that code instances for which the answer is yes. Typically, as we did for Turing machines, our coding allows certain strings that are flawed. They don't really represent an instance. We'll always assume that flawed encodings represent instances for which the answer is no. For example, as a problem, the language LD can be stated, does this Turing machine not accept its own code? When we talk about problems, we use the term decidable. It means that there is an algorithm to answer its question. That is, a Turing machine that accepts the encoded instances of the problem for which the answer is yes, and also halts without accepting the other instances. So a decidable problem is really the same thing as a recursive language, if we think of the language as encoding a problem. The opposite of decidable is undecidable. So here's what we know about languages so far. In the center we see the recursive languages, or as problems, the decidable problems. Then there is a superset of the recursive language called the recursively enumerable languages. These, recall, are the languages accepted by Turing machines with no guarantee that they will halt on inputs they never accept. And then there is outer space, the uncountably many languages that are not recursively enumerable. They have no Turing machine at all. So far we have one example of a language, L sub D, that lives in this region. Remember that the undecidable problems are all those in either the second ring, the recursively enumerable but not recursive languages, or in outer space, that is, everything that is not yellow in this diagram. And a big question we need to answer, are there any languages in the second ring, those that are recursively enumerable but not recursive? And remember, the real goal of our plan is to show some real problems that are undecidable. The fact that L sub D is undecidable, and in fact super undecidable because it is not even recursively enumerable, is interesting, but it doesn't by itself tell us anything about the real world. So here are some examples of real problems that are undecidable. Will a program ever reach a particular line of code? Is a given context-free grammar ambiguous? Are two given grammars equivalent in the sense that they generate the same language? But still staying within the world of Turing machines rather than the real world, but a necessary way station on our trek to the real world, is to show a particular language to be recursively enumerable but not recursive. This is the language we call L sub U, the Universal Turing Machine language. In more detail, the Universal Turing Machine takes as input a binary string consisting of the code for some Turing machine M and some input W for M. The Universal Turing Machine accepts the coded M and W if and only if M accepts W. The idea of the Universal Turing Machine should not seem strange if you've ever contemplated a Java virtual machine. The JVM takes a coded Java program and an input for that program and executes the program on the input. In fact, the JVM is more general in capability than a Turing machine, which can only make a single accept output. The JVM can cause whatever output the program calls for it to be made. So let's see how to build a universal Turing machine. First of all, inputs to the universal Turing machine are of the form a code for machine M, 3 ones, and then the binary string W. Since a valid code for M can never have 3 consecutive ones, it is never ambiguous what part of the input to the universal Turing machine is M and what part is W. The universal Turing machine accepts its input if and only if that input has a valid code for some Turing machine M and that Turing machine accepts W. So for example, the universal machine never accepts a string that doesn't have 3 consecutive ones. We'll design the universal Turing machine as a multi-tape machine. The first tape will hold the input and we never change that. The second tape is used to represent the current tape of M during the simulation of M with input W. We'll discuss this representation shortly. The third tape of the universal machine simply represents the state of M. The first thing that the universal machine needs to do is to examine its input, and particularly that portion that represents M. It has to check that between consecutive double ones there are always 5 blocks of zeros, and it also has to check that a block of 3 ones appears somewhere on its input, and regards this as the end of the rules for M. Finally, since M is assumed deterministic, the universal machine needs to check that there are never 2 rules that agree on the first 2 components. All this checking will require running back and forth on the input quite a bit. It can be facilitated by copying blocks of zeros onto one of the other tapes and comparing these with the rest of the representation for M. If any flaws are found with this code for M, or the 111 is not found, then M is regarded as a Turing machine that accepts nothing, so the universal Turing machine immediately halts and rejects its input. Assuming the code for M is valid, the universal Turing machine next examines the code for M to determine how many squares of its own tape it needs to represent one symbol of M's tape. That is, we discover the longest block of zeros representing a tape symbol, and add 1 to that for a marker between symbols of M's tape. Thus, if say x7 is the highest numbered symbol, then we'll use 8 squares to represent one symbol of M. Symbol xi will be represented by I zeros and 7 minus I blanks, followed by a marker #. For example, here's how we'd represent x5. 5 zeros, 2 blanks, and then the #. Now initialize tape 2 to represent the input W. Remember, zeros are x1 and ones are x2. The blanks on the second tape of the universal machine all represent x3, the blank of M, but we won't initialize those squares until we need to. Finally, we initialize tape 3 to hold the start state. That state is always Q1, so it is represented by a single 0. Now we're ready to simulate M. We have the current state on tape 3 and the tape of M represented on tape 2. We scan the moves of M on tape 1 until we find a move that matches both the state and this tape symbol. If we can't find one, then apparently M halts without accepting W, so the universal machine does so as well. But if we find a match, we'll find Right after that, on tape 1, the new state, which we install on tape 3, replacing the old state. We also find a new tape symbol with which to replace the old tape symbol under the head on tape 2. And we also move the tape head one simulated square of M's tape, left or right, whichever the move says. And most important, if M enters an accepting state, then the universal machine stops simulating and accepts its own input, which, remember, is the pair machine M plus input string W. We claim that the language L sub u is recursively enumerable but not recursive. We just showed that there is a Turing machine for the language L sub u, so surely LU is recursively enumerable. But suppose L sub u were recursive. That means there is a Turing machine that always halts and whose language is L sub u. If that were the case, then L sub d, the diagonalization language, would also be recursive. We're going to explain why on the next slide. But we already know that L sub d isn't recursively enumerable, let alone recursive. So let's assume that L sub u is recursive. We construct an algorithm for L sub d as follows. We're given an input W. Let's suppose W is the ith string. The first thing to do is to check whether or not W is a valid code for a Turing machine. For example, that it doesn't have 3 consecutive ones. If the code is not a valid string, then the ith Turing machine defines the empty language. That means W, the ith string, is not in the language of the ith Turing machine. Therefore, W is in L sub d. Now, suppose W is a valid code for a Turing machine. Then simulate the hypothetical algorithm for L sub u on the input W111W. That bit string represents the ith Turing machine processing the input that is the ith string. Eventually, this algorithm will halt and tell us whether or not the ith machine accepts the ith string. If the algorithm says yes, the ith machine accepts the ith string, then we say no, because that means W is not in L sub d. However, if the hypothetical algorithm says no, then we accept W, because W is in L sub d. We proved that there is no algorithm or any kind of Turing machine for L sub d. Therefore, we must blame our assumption. The only thing we assumed without proof was that there is an algorithm for L sub u. That means there really is no algorithm for L sub u. Put these facts together and we conclude that L sub u is really recursively enumerable but not recursive. So here is our improved version of the universe of languages. We still have the decidable problems, or equivalently recursive languages, in the center. Outside, there are 2 kinds of undecidable problems. The second ring is the languages that are recursively enumerable but not recursive. We now have a concrete example of such a problem, L sub u, the universal Turing machine language. And beyond that is the not recursively enumerable languages, of which we have one concrete example, L sub d.